Okay, I want to talk about your only option for continuing to solve a problem if you use the x is small approximation, the x is not small enough. So when you get to the testing stage, you're not less than equal to 5%. But you don't have the option to go back and say brute force through a quadratic formula. So I'm going to look at the same example that we did in the previous video. So this H2S gas, 2 of those in equilibrium with 2 H2 and 1 S2. And we are going to find the equilibrium concentrations of all components. When the initial concentration of H2S is equal to 2.50 times 10 to the minus 4th. And it's the same reaction under the same conditions. So my equilibrium constant is still 1.67 times 10 to the minus 7th at 800 degrees. So let's get our race table set up. I've got the reaction already. My initial H2S is 2.5 times 10 to the minus 4th, 0, 0. I have to go to the right, so minus 2x plus 2x and x. And now my equilibrium row is 2.5 times 10 to the minus 4th minus 2x, 2x and x. So once again, if I were to set this up, I would end up with a cubic root that I cannot solve, especially not with the calculators that we have. But, I mean, I'm close to equilibrium, potentially. So let's do the same comparison, right? My KEQ is on the order of 10 to the minus 7. My reactant concentrations are on the order of 10 to the minus 4th. So small KEQ, I'm only going to make a little bit of product. I pretty much have all reactant, right? I don't have any products to start out. These are apart by 10 to the 3rd. Okay, so it's exactly equal to that comparison that I said you could do. And we really don't have any other options. So we should go forward with this and see what happens. So I am going to assume that x is small. I will go ahead and set up what my problem would look like without that removed, right? So I've got my products, 2x quantity squared times x, and then it's going to be 2.5 times 10 to the minus 4th minus 2x, this whole thing squared, equals 1.67 times 10 to the minus 7th. So if x is small, then 2.5 times 10 to the minus 4th minus 2x is basically equal to 2.5 times 10 to the minus 4. So x is small eliminates that minus 2x part. And I'm back to something that I have the ability to solve, right? So I will have 4x cubed over 2.5 times 10 to the minus 4th squared equals 1.67 times 10 to the minus 7th. So if I go through and solve all of this, I end up with an x value of 1.38 times 10 to the minus 5th. So I test this, right? And it's the value of x divided by the number that x was subtracted from or added to times 100. And I get, 5.52%. So we were so close, but it was not a good assumption. And like I said earlier, we don't have the choice of going back to try to just solve it with quadratic or anything like that because we have a cubic root in this problem. So what we do here is something called successive approximations. So 1.38 times 10 to the minus fifth is not close enough to the actual value of x, but it might be a good starting point approximation. So what I'm going to do, I'm going to now label this x1, and let's get this circled in a color, and we'll go purple. So this is my starting point for approximating what x would be. And I'm going to take this x value and plug it in to the point where I had removed x from the equation, and then I'm going to solve for my x cubed again. So what this looks like, so that was the first value of x. I'm going to find a second approximation for the value of x, which means I still have 2x squared, I still have x, but I now have, I'll put this in brackets, 2.5 times 10 to the minus fourth minus 2 times the x1 value that I just had, 1.38 times 10 to the minus fifth. And that entire quantity squared equals 1.67 times 10 to the minus seventh. All right. If I solve for x here, so I'm going to call this x2, I get 1.27 times 10 to the minus fifth. And so, okay, we have some other x value. We need to know what to do with it from here. Well, the answer is that you plug it in again, right? So we will successively approximate x and keep going until the values converge. It's not as bad as it sounds. Let's plug this in one more time. Again, I'll put this in, we'll color it in blue. So I'm going to go back to my original equation. We're going to find the third approximated value for x, and 2x squared times x divided by 2.5 times 10 to the minus fourth minus 2 times, now I'm plugging in my second value for x, 1.27 times 10 to the minus fifth. This whole quantity squared equals 1.67 times 10 to the minus seventh. When I find x here, I get 1.28 times 10 to the minus fifth. That's great. These are so close to each other in value. If I had gotten 1.26, that would have also been fine. So that means that x3, this 1.28, is the x value that I will carry forward to finish solving the problem, because remember, we haven't actually finished solving the problem yet. All we've done is find our x value. So I can use x equals 1.28 times 10 to the minus fifth to find my equilibrium concentrations, right? So for H2S, That means 2.54, or not 54, 2.5 times 10 to the minus 4 minus 2x. For H2, that means 2x. And for S2, it's just equal to x. So put a unit on that one. The H2S is 2.24 times 10 to the minus 4th molar. And the H2 is 2.56 times 10 to the minus 5th molar. So these three values are my actual final answers for this problem. As you can see, with the amount of algebra that goes into this, it's hard to feel comfortable knowing that you're on the right track. So if you have reached X6 or so in your approximations, go back and check your work. So you should not have to do this more than 4 or 5 times to converge on a number.